Okay, on this slide, we talked about a parallelism tolerance defines the allowable orientation variation between the tolerance feature and the reference datum feature, but does not affect location or size of those features. The next slide illustrates this point. Okay, so what we have here is we have a prismatic block. We have a datum A, which is the lower surface. Here we have a feature of size, which is a thickness, 438 plus or minus 10 thousandths. And then, we have the parallelism tolerance here of 9 thousandths to A. Okay, so what we're showing here is we have the perfect form envelope at MMC. This is the 448. That would be the maximum thickness. Okay, here we're showing our distance between two parallel planes. So our flatness tolerance, our parallelism tolerance is this 9 thousandths, okay, and it goes from the max to the min of the size of our part. Okay, as we can see, our size is not at the max. Okay, so what we're saying here is this 9 thousandths applies to the max and the min of these surface elements. Okay, so the orientation tolerance is created by two planes parallel to datum A based upon the max surface elements here and then the min surface elements. Okay, so it's not tied to the size tolerance. Now, how would we check parallelism on a flat surface? And here's how we would do this. Okay, so what we have is we have a surface plate and we put our workpiece down on the surface plate. This surface plate simulates datum A. Okay, and then what we do is we run our dial indicator over the surface of the workpiece, and as long as the dial indicator didn't move by any more than 9 thousandths, our part is good. Okay, so we have the surface plate simulates datum A, and then our dial indicator checks the parallelism of the opposite surface. That is how parallelism on a flat surface is checked. Okay, so let's talk about parallelism interpretation of a cylinder. Okay, so in this case we have a link. Okay, our link has a positional tolerance here. The 1.5 is our basic dimension, and then that is from one hole to the next hole. Our holes are 375 plus 5 minus nothing. We have a positional tolerance here that applies at maximum material condition and at maximum material boundary, and then we have the parallelism. So what we're trying to achieve here is we're trying to achieve a parallelism between these two holes within this boundary, the location boundary. Okay, so what does it say? It says we have a cylindrical zone when the hole is at MMC. That's our orientation tolerance. Okay, then the axis of tolerance zone is parallel to the datum axis B tolerance. So what we do is we find the datum axis B tolerance, datum axis B, and we make sure that datum axis here is parallel to datum axis B. So that's how a parallelism tolerance is applied to cylinders. Now, how can we check this? Okay, so what happens here is our parallelism has to do with the features of the holes, regardless of really where they're at. Okay, so in this tolerance up here, what we have is we have 28 thousandths in maximum material condition. We have 28 thousandths positional tolerance. Okay, so this gauge here, we'll call this a functional gauge. This functional gauge is going to check the parallelism, but it's not going to check the position tolerance of the two holes. So we have a movable element here on our position gauge. In this case, the diameter here is 250. Where am I getting 250 from? 250. That's the MMC of the datum hole. Okay, that's right here. That's 250. That's the MMC of the hole. So this is the 250 of the hole, is the maximum material condition of the hole. That's the size of this gauge pin. And then the size of this gauge pin here will be the virtual condition, which will be 375, which is our maximum material condition, minus 9 thousandths here, which gives us 366. So there's our virtual condition of the hole. So if this part fits on this gauge with the adjustable to adjust for the location tolerances of the hole, we know we have achieved the parallelism of these features relative to each other. So that's how we would check parallelism of a feature of size. Okay, so let's talk a little bit about perpendicularity. Okay, so really on a drawing, we actually imply, if we put a drawing out here like this, we're implying that, hey, there's 90 degrees between these two sides. Okay, that's really what we're applying. And then if we looked at the block tolerance, like we're talking about here, the block tolerance on an angle is plus or minus a half of degree. Okay, so here is what that means. It means, well, here's this size here, here's this size here, and then the angle between those two features will be 90 plus or minus half a degree based on the block tolerance. Okay? So then, if we were to apply a perpendicularity tolerance, okay, we define one surface as datum A, and we define a perpendicularity tolerance on the other surface with respect to datum A. So essentially what we have here is our implied 90 degrees here is now a basic dimension. Okay, we don't have to put it down as a basic dimension because it's implied, but what this means is that the 90 degree, the perpendicularity between these two planes is now a basic dimension, and the tolerance upon that feature actually becomes this tolerance in the feature control frame right here. So that's what perpendicularity means in terms of implying a 90 degree tolerance. Okay, so 90 degree dimension is not required in the orthographic views. The tolerance must be specified in the feature control frame, and the feature control frame is placed either on an extension line or a leader to the surface. Okay, so in this case we applied the tolerance to the extension line. And then the tolerance must reference datum. You can't have a perpendicularity tolerance without a datum. You can't have an angularity tolerance without a datum. You can't have a parallelism tolerance without a datum. So all of these orientations, tolerances, need at least one datum. Okay. Here's perpendicularity of a surface. What does that mean? Okay, so what we have here is we have datum A to this lower surface, we have a feature of size here, and then we have this perpendicularity tolerance applied to this surface. What does that mean? Okay, so first of all, what we have here is we have our 203, that is our perfect form at maximum material condition tolerance. As we can see, this part here is somewhat short of the 203, which is good. That applies. That means we're allowed to use our perpendicularity tolerance. We have a perpendicularity tolerance of 5 thousandths, so that gives us 5 thousandths between two planes perpendicular to datum A. We have our datum A. Datum A is simulated by this surface right here, and then based on our high spots of our surface, we have 5 thousandths tolerance. Okay, so how would we check such an item? Okay, here's what we would do. We would take that block, we would mount that block, clamp it in a rotated position to give us a good reading. Datum feature A is clamped to a datum feature A simulator. There you go, there's your simulator for datum A. There's our surface plate, and then we run our indicator over the surface, and as long as the indicator doesn't move by more than 5 thousandths, we have met our perpendicularity tolerance. So that's how we check a perpendicularity tolerance. Okay, I'm going to pick this up in the next movie.